Okay, good evening, everyone. So, can you guys hear me? Okay, great. So, let's hope that it won't be interrupted like what happened the other day. I have restarted the machine, and hopefully, I'm on a good network. All right. So, my goal today is to talk about Dijkstra's algorithm. And then we will talk about this shortest path tree concept. Okay, single so shortest path idea. So the main lecture today is all about finding shortest path. Given a graph, you want to find the shortest path between a given node and another node. Okay, so we'll talk about what algorithms might be appropriate for doing such things. Okay, so first of all, I want to kind of make sure you read these announcements. So there's an announcement on the LSC pre-grading, some main method issues. So you should go and look at it on the announcements. And also there's an announcement on delay 1 and test 1 grading, also test 1 grade stats, and test 1 grades published on GradeScore, and LSC pre-grading that came on April 15th, and also now the programming assignment on the friendship graph algorithms. Okay, so I just want to mention you that you should read those announcements to just keep track of what's going on in the course, because we are all online now. It becomes even more important for you to keep up with it. So as you know, there's a test coming up this Sunday. So that will cover the binary trees, Huffman coding, and hash tables. And the main things are the problem set 8 and problem set 9. The format is going to be similar to April 5th test. And since you have done this before, hopefully this time it'll be okay. So there's also a late submission period from 2 to 2:15. So just follow the same rules and things that you did with the previous test. All right. So I hope you will study these things over the weekend, and be prepared for that test. Okay. And notice that it's going to be releasing 11:50 a.m. So just before noon, and then it's ending at 2 p.m. So you want to make sure that you set up an alarm or something on your phone so that you know the test is beginning. Okay, so you don't want to skip that. All right, exam will be out of 45 points, but we're going to double that it's going to be 9% of your grade, essentially 90 points. Okay. All right. Let me just get this thing out of here. All right. All right. So let's just take a look at some of the questions that from the problem sets. For instance, that I'm going to spend 5-10 minutes on this, and then we'll go to the shortest path algorithm. Just a reminder. So in this case, the strings are represented by a trie. Trie is essentially like this is a binary kind of a tree. If you go left, it'll be a 0. If you go right, it'll be a 1. So you could have the strings represented as 0, 1, 0, or just 1, or 1, 0, 0, or you can have 1, 0, 1, 1. And so basically that 1 is kind of like a prefix of both of these strings. So 1x kind of denotes the end of a string, and you can still go to the left. So this will be 0, and this will be 0. So that's why you get 1, 0, 0, right? So this will be 1. This will be 1. Okay. Just something really simple. And then if you recall the Huffman compression. Let's suppose that we have 7 characters each with frequency n each. So let me ask you the first question. What's the size of the uncompressed file in bytes? Can you type the answer into the chat room? Okay, 7n. Okay, very good. So 7n without compression. Now, if you compress it, it's going to look very interesting, because what we're going to do is that we take the 2 lowest ones, because all of them are n, right? So because they all have n frequency, they all have equal frequency. So we'll build a tree like this where the root is 2n. And then 2n is, so we have in our, originally we had this in the priority queue, 7 characters with n each. And now we took 2 of them out. And then we got a new one now. Will be, so n, 5 n's and 2 n, right? So that's going to be in the priority queue. So when you get the next 2, you're going to get another 3. So we get 2n here. So now we have removed these and put another 2n into the queue. So when you get the next 2, you're going to get another tree like this. Okay, so you're going to get that. So this is gone. So it'll be like 2n here. All right. So that's any questions so far? Okay. So we only have now in our priority queue, we have the next 2 minimums are the n and 2n. So we will take n and one of these 2 n's and then combine them to get 3n. Okay, maybe I should have some space here. So we'll have n and 2n to get 3n. Okay, and then in your priority queue now you have 3n, 2n, and 2n. And so the next 2 you're going to get are the 2n, because those are the 2 minimums. So that'll give you 4n total. And then you only have 2 things in the priority queue now, which are 3n and 4n. So you're going to get these 7n. All right. So if you encode the characters, so if you say this is A, B, C, D, E, F, G, those are the 7 characters. Each of the characters now take how many bits to encode? Some of them take 2, right? So the A takes 2. So A is the last one. This takes 2, right? So you have 0, 0. This is 1, 1, 0, 0, 0, 1, 1, 1, 0, 1. Okay. So we have one of them going to be 1 character. A is going to require 2 bits, right? And all the other ones, if I believe, are 3 bits. So B through G are 3 bits each. Okay. So the total number now is going to be 2 bits. So in bits we can compute, because there are n characters. So for A it will take us this much, and then we have 6 other characters, and each one has n things, and we will encode that with 3 bits. Okay, so you can just say this is 56n in bits. Sometimes keeping it in bits makes it make more sense. And this one will be, this is the compressed file in bits. Okay, any questions? All right. So basically, I think we have the size of the files. This will be like, if you actually compute this, that would be 20n, right? That's the total. So the ratio, compression ratio for this particular problem would be 20n divided by 56n. And that gives you 20 over 56n cancel out. So that's like I can divide by something. So let's say 20 or 56. You can simplify that. Notice that the compression ratio is about slightly better than half. Okay. Any questions? By the way, I think this file is available on. Okay, so let's move on. So let's do a hash table thing. Let's suppose that we want to insert this hash table into a table of size 10. So table of size 10 means that so I have 0, 1, 2, 3, 4, 5, 6. Oops, I need a few more here. 8 and 9. Okay, so where does 45 go? Okay, 5, because you take the mod 10. Okay, I apologize. The very sensitive to touch here, so let me just go back to the page width. All right, so 45 goes into 5. Okay, so that's where 45 is going to go. I'm just going to put it in at the end, although you are really, and 65 also go there. Okay, now usually you will insert 65 at the beginning because you don't want to spend too much time doing it. Because, but at the end when you're searching for it, whether it's hard to say which one you're going to be searching for. You're going to be searching 45 or 65, right? So it depends. I mean, it doesn't matter. You just put it in the front. 32 goes into this one here, 32, and 12 goes into also this one because you take the mod 10. 60 goes into this one, and then 23 goes into this one. Okay. Now, I like you to, let's suppose that when you look at this table, the load factor. So what's the load factor for this table? So the hash function gives you the hash code. So the hash code is the 65, 45, and so we don't know how we got those things. Let's assume that you have hash codes, right? But you always have to mod with the table size. So let's see. So what's the size of the table? It's going to be 6 over 6 keys and 10 spaces, and so it's 0.6. Okay. So that's going to be the size of the load factor for this. Now, suppose because we know the load factor, maybe we could make the table a little bit smaller. Okay, let's make it 5. So that means we have to rehash. Now, if you rehash these keys, take just a minute to see where these things go if you rehash them. Okay, now what we're going to do is we're going to do mod 5. We have to assume that the hash codes are the same. Okay, so the hash codes are 60, 32. They might have keys or something, but let's just assume that the hash code and the key are the same thing here. Okay, so 60, if you mod with the 5, still go here. 45, if you mod with the 5, goes here. Right, 65 goes here. Again, I didn't really consider the order here. 32 mod with the 5 goes to 2. That's it? Yeah, I think 2, right? Okay. 32. 12 also goes there. And 60, you already did that. 23 goes into 3. All right, so that's what I get. Do you have any questions there? Okay, so what's the load factor now? The load factor is going to be what? Yeah, so it's going to be 6 out of 5. So load factor is slightly more than more than 1, right? So load factor now is bigger than 1, which is kind of good because you want 1.2. Okay, so you want sort of like you want it to be bigger than 1. Okay, you don't want to be less than 1 because then it's just you're wasting a lot of space. Okay, so you want it to be slightly, usually about 2 or 3 is good for the load factor. Okay, so going forward, studying for your exam, maybe you should take a look at PS2 and PS8 and PS9. That can be helpful. Yeah, so usually what you do is when you rehash, yes, you have to take the original nodes. You don't have to recreate the nodes, but you take their pointers and compute the new position and insert it to the new table. Okay, load factor indicates how crowded the table is. So for example, if load factor is like 10, that means the chain length is 10, right? The average chain length is 10. That might be too much because you don't want to spend too much time searching for things. Okay, great. Let's move on to our main topic today. So, okay, so I'm going to start with a very interesting problem. In fact, like I said, this is the sort of the most interesting topic of this course, the graph theory or graphs, because they're so common in applications. So there's a famous problem called traveling salesman problem. Okay, so the traveling salesman problem says the following. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city and returns to the original city? That means you don't want to go through the same city twice. You want to touch every city. For example, one can start from here, a traveling salesman, and cover all the cities, obviously, because being a salesman, you want to save time. So you would find the shortest path from going to cover all the cities, right? So I have a question for you. So if there are n cities, okay, how many possible paths are there? Okay, so if there are n cities, there are n factorial possible paths. Not all of them are possible. Like, for example, if you take like, this is really the number of permutations. This is called the number of permutations you can get. Like, for example, 1, 2, 3, you can have 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, and then 3, 1, 2, 3, 2, 1. So there are 6 permutations coming from 3 cities. If you name the cities 1, 2, 3, then you get 6 permutations. All right. And it's not going to be you will have like it could be n minus 1. Yes, that's true. But because n is so large, we don't even care about that. Okay. So this is 3 times 2 times 1. Those are the 6 things that we wrote down here. Okay, so if you have 4 cities, you will have 4 times that. That's going to be 24, and then you multiply it by 5. That would be, I think, like 120 or something, right? So it gets very, very large. All right, and the problem with the n factorial is like when you go beyond like 30 factorial, this is huge. Okay, computers cannot even think about processing that because it's just too big. All right, now in computer science, we call these things what's called the NP-hard problems. Okay, NP-hard problems, although we are not going to go into theory here, I just want to get you familiar with the concepts of which you might find in future courses. Okay, in theory courses, you might run into these things. Like we call it non-deterministic polynomial time. Okay, so these are the set of decision problems that are solvable in polynomial time. When we say polynomial time, we think about n squared or n cubed or any kind of polynomial. Okay, we know even anything beyond n squared is too bad, too slow, but still we say, okay, it's polynomial time. and then by what's called a non-deterministic Turing machine. Now, again, I don't know how many of you are familiar with the idea of Turing machine. Turing machine is the model of a machine that is the basis, that's the mathematical basis for the modern machine. Okay, so a Turing machine had a tape and a controller and all that, which is what we have. We have memory and a processor, right? I have a lecture. This is one of my lectures from Discrete Structures on Turing machines, so you can take a look at it if you like. It says that there are lots of hard problems that the computers cannot solve yet, but the solution to the problems can be verified in polynomial time, okay, by a machine. Here you can replace the Turing machine by just a machine, whatever machine you know at this point, okay? So for example, subset sum problem. In other words, given a set of numbers, okay, let's suppose you have n numbers, okay? Now let's take some sum, okay? Let's say some sum between, let's say, maybe it's bigger than n, less than, I don't know, 2n or something, right? So you might ask the question, how many elements of 3 things, like, can I take from this set, right? That will give you some sum. For example, I have this set of n things. I want to find 3 things at a time, right? A2, A3, A4, and their sum always come to S, right? So let me ask you the question, how many possible pairs of 3 can I choose from n things? Okay, very good. So the answer is n choose 3. Okay, the factorial over 3 factorial and n minus factorial. So note that this subset sum problem is very, very hard. Like factorial. Factorial is not polynomial time. Okay. All right. So that in general, these shortest path problems are really hard. Okay. This is very, very hard. You can see that. This traveling salesman problem still not being solved. All right. And because it doesn't have a polynomial time algorithm. It doesn't have an n squared, n cubed, or even n to the 100 solution. It doesn't have that. Okay, solution only can be expressed in terms of some kind of factorial. Okay, so we're going to talk about what's called the single source shortest path. So let me give you kind of like a definition of this. Okay, so the definition of this is going to be, I get my thing organized here. So given, oops, I'm not doing well here. Given a source node S, find the shortest path from S to every other node. Okay, every other node. So what this says is that given a source node S, okay, so start from somewhere, and then find the shortest path from S to every other node. All right, so let's take a look at how we can do that. So here's an example. Now, so let's say that I pick my S to be 3. Okay, the node 3. And I want to find from S to the shortest path to every other node. So in other words, in this case, I'm defining the shortest path like it's an unweighted graph. Okay, therefore, shortest path is defined as the number of edges. So each one, you can imagine, each one has a weight 1. They are all equally likely, perhaps, okay? So we can have all things like weight 1. We just don't, you can think about an airline graph or something where you just care whether there's an edge or not. So if you count the shortest path to 1 from 3 would be 1, to 2 would be 1, right? 1. Oops. And 4 is 1, 6 is 1, and 0 is 1. But for the 5, it would be 2. Okay, so these are the shortest paths from 3 to every other node. Now, clearly, I can see the graph, so I can just mark it up. And that's not what we're looking for. We are looking for an algorithm. Okay. Okay. So what's the, yeah. So I would like you to take a minute to mark the shortest path from 1 to every other node in this graph. That should be, hopefully you'll quickly figure that out. Okay, I'll wait for someone to give me one answer. Okay, so that's one answer. So let's just get started. So clearly that would be 1. Okay, there are more coming in, so good. Keep typing if you're done with it. 1 here, 1 here, 2, and 2, and 3. All right, so those are the shortest paths that you get by doing this. Now, what does this remind you? What algorithm does this remind you? Not Dijkstra, it's BFS. That's correct. Okay, so this is really what we really did was this, right? We did BFS and we did a level order traversal, and we got that. So you might imagine when you have the unweighted, undirected graph, you can do BFS on that. Okay, BFS on that to compute this. So let's do an example here. So here's the sort of the way we think about it, okay, as an algorithm. Okay, we are doing BFS clearly. In this case, I have a directed graph. Okay, so what I'm going to do is I'm going to maintain an array called distance2. Okay, what this array will do is it will maintain the distance to the, so we have, let's say we have 1, 2, 3, 4, 5, 6, 7, 8. Those are the nodes. Okay, and I will start from node number 3. Okay, I'll start from node number 3, and then here's what I'm going to do. Okay, here's the algorithm. Okay, so when you do BFS, as you recall, we use a queue. Okay, we enqueue the source vertex. So we dequeue that vertex, the first one in the queue, and then we find all the things that are adjacent to that vertex V. We call them W. In this case, we add a little bit of a thing here. Okay, so here's how the process will start. I'm going to start from 3. So I'm going to say the distance from 3 to 3 is 0. And I'm going to assume that all the other distances are infinity. Okay, because I haven't considered anything yet. I have no idea what these distances are going to be. Okay, let's assume all the other distances are infinity. So what I'm going to do is my node 3 is in the queue. So I dequeue that, and then I get that. So let me draw the queue here. So we have 3. I'm going to dequeue that and then add the adjacency things into that. Okay, adjacency things into that. So 5 and 1 are there. So then what I do is I take all of the W's in the adjacency list and then look at the distance to. So I look at the distance to W. Like, for example, in the adjacency list, I find 5 and 1, and I find the distance to 5 would be infinity. And that's bigger than the distance to V plus 1. So what is the distance? Then what I do is I set the distance to W to distance to V plus 1. So what does that mean? That means that distance to V is 0. Okay, right now V is the 3. So I set that to 0. So therefore, I'm just going to update this one 1 and 5. Okay, because infinity is bigger than 0 plus 1, and therefore they get new values. Do you have any questions? Okay, so we call this sort of relaxing the edges. Yeah, that's right. The previous vertex, that's true. I'm not saving the path. Okay, I'm just looking for the shortest distances. So in fact, ideally we have something called edge to. Okay, so what we mean by edge to means we are saying that we updated this thing because there was an edge from 3. Okay, 3 to 1. All right, so that's the previous vertex. There's an edge from 3 to 1, and for this one we updated this to be 3 as well because there's an edge from 3 to 1. Okay, so now what we're going to do is we're going to take the next thing from the priority queue, which is 5, and then we're going to insert the 4 and the 2. Those are the 2 adjacent things in the list. Okay, now what we're going to do is we're going to, now clearly this is the way you're thinking about, right? This is infinity and this is infinity. Okay, 4 and 2 have infinite distance right now. But what are the new distances of 4 and 2 based on this algorithm? Okay, new distances are going to be 2 because the 4, okay, is infinity, but it's smaller than 1 plus 1, right? Because the distance to 5 would be 1, plus another one would give you the distance to 4. So this is going to be 2, and this is going to be 2. What is the edge to for 2 and 4? It's going to be 5. So because we updated this thing based on the edge from that. Okay. So now what we're going to do is, so we call this, we process these links. Okay, those edges are processed. We're going to get the next thing from the priority queue, which is, queue, which is 1. It's not a priority queue, it's just a queue, right? 1. So from 1, I find an adjacency node 7. Okay. Now, so what I'm going to do is, because I know the distance to 1 is 1, and then if I add another one, it will be distance to 7. That would be 2, which is less than infinity. In this case, that 2 was obtained by, I came from 1 to get that distance. Okay. So now I say this is processed. Let's now go to 4. Okay, when I go to 4, I will have things connected to 4 are 6. Okay, so I'm going to put the 6 to the queue, and then I will update the distance to 6 based on the distance to 4. Distance to 4 is 2, plus 1 gives you 3 as the distance to 6, which is less than infinity. All right, and but I came to 6 from 4. Okay, so the edge came from 4, so I'm going to write 4 for that. Any questions? All right, let's do a few more. And then I go to 2, and I want to put, but 2 to 6, there's a link, but 6 is already there, so I don't have to do that, anything. Okay, and then I process 7. 7 will bring 8 into it, but because of 7, I could update the 8, right? So the 8 is going to be updated with 3, and it came from 7. All right. So now now let me ask you the question. I did not update this link from 7 to 2. I didn't relax it. Why didn't I do that? Yeah, so 2 was already visited. So if you had already gone there, you couldn't find a shorter path. Okay, you couldn't find a shorter path because you've already been there. But remember, that's not the case if there was a weight associated with these things. Like, for example, it is possible that if there are weights, maybe this was 2, this was 3, and this was 1, this was 1, this was 1. So in that case, the original one would be 5, but we have a better path, 1 plus 1 plus 1 to 2. It's a longer path, but it's a shorter path, okay? So if you have some weights, it's going to change how we think about this. Here, right now, because every node here is now relaxed, okay, and that means it has a number associated with it, we actually found the shortest path, okay? So if someone asks you, what is the shortest path to 6 from 3? Okay, let's say this is the source vertex, and this is the destination vertex, right? Can you tell me the path, the shortest path, the nodes in the shortest path from 3 to 6? Okay, say 3, 5, 4, 6. Okay, let's see how did we find that? So remember, 6 is the destination, right? How did we get to 6? We got to 6 from 4. How did we get to 4? We got to 4 from 5. Okay, how did we get to 5? We got to 5 from 3. All right, so if you take the path 3 to 5, 5 to 4, 4 to 6, that's how you get the actual path. So it's sort of like a backtracking kind of an algorithm, right? So essentially you are saving the previous. So in order to get the path, I only need to know how I came to the shortest path from which node did I come from. That's very important. Okay, 3, 5, 4, 6. Can you do the same can you find the shortest path to 8? Okay, 3, 1, 7, 8. Okay, so we have 8. We came to 8 from 7. We came to 7 from 1. We came to 1 from 3. And that's it. All right, so that's the path. Any other questions there? Okay. All right, so let's ask, it's an important thing to notice here. The unweighted graph, breadth first search guarantees that when we first make it to a node V, we can be sure that we have found the shortest path to it. So therefore, we don't really need to do anything there. So the question is, what what is the runtime of this algorithm? Yeah, so the runtime of the algorithm is V plus C because it's pretty much like the breadth first search. We didn't do anything fancy here. We just computed some distances, maybe did some comparisons, but we really, this is big O of one, right? We didn't really do anything much there. So if you remove that computation part, you have breadth first search. Essentially, if you remove that, okay. Okay, I'm going to skip that. So you go to the next one. I will leave that for you to do. Okay, so the next thing I like to do is to show you kind of like a very cool demo of Dijkstra's algorithm. Okay, so before I explain to you what Dijkstra's algorithm is, I'm going to show you this Dijkstra's algorithm. So give me a minute to set it up here. So let me just hold on one second here. Now I did send you, in case you have a Windows machine. I would think that this only runs on Windows machines because it does have some dependencies. So I'm going to try to share another thing. Oops, what happened to it? Okay. So the what I'm going to show you is what's called the Dijkstra's algorithm. But the power of this pad, which I call the smart paper. So the smart paper is that I can draw a graph and apply the Dijkstra's algorithm to find the shortest path. So I'm using my stylus to draw things. So I draw a circle, draw another circle. Oops, not really. What's going on here? Oops, something is going on. Hold on one second here. Not perfect. It's not okay. Let me just stop that. Fortunately, it's not. For some reason, because I'm sharing the. Didn't realize that. Okay, maybe I could be careful here. I'm going to give it a try, although it's a little frustrating now, right now. That's fine, yeah. We'll do here. Okay. Unfortunately, I didn't. Okay, I may have to switch to the other computer to do this. You guys see this? Okay. Yeah, okay, you see the screen, but unfortunately, I think you're right. I won't be able to do it because my pen is not synchronized with the pad. Okay. Otherwise, this works beautiful way. I think it's the way perhaps the Sakai share the screen. Anyway, so we'll not worry about that. Okay. And if you really want to see how this works, just watch the video I sent the other day. I think it'll show you the idea. Okay. So I'm going to stop share and then go back to the other thing here. Okay. Let's see here. Okay, so this kind of shows me, why I have to be in the class to do this, because it doesn't really sync well with this platform, that I cannot demonstrate it using the same ideas. So the program that I was going to show you, it kind of falls into what area called pen-based computing. And there's a website I sent you. If you're interested in talking about it, you can talk to me after the semester is over. And the idea is that to kind of like you have this smart paper that you can draw anything. So you can imagine you have a math paper, you can just draw write an equation, and it'll solve the equation for you. Right? So you just interact with paper just like you interact with a paper and a pencil. The only difference is that the program is able to recognize your strokes and interpret them and apply whatever the operations. The thing I was going to show you, in fact, does the same thing. I can just draw a graph and provide some weights to the graph, and then ask the graph to find the shortest path. Okay. All right. So what is Dijkstra's algorithm? So the Dijkstra's algorithm is applied to a directed weighted graph. Weighted means that the weights are there. Okay, so you can see in this graph, you have 5, 15, 8, 9, and so on. Now, the Dijkstra's algorithm works just like the other one I did. All right, so let me do the same thing. So I have two arrays. One is called edge2, the other one is called distance2. And then I have the nodes. Let's see, 1, 2, 7, up to 7. Okay. So we have these nodes. And let's suppose that I start from 0. Okay. Just like the other one, what I'm going to do is I'm going to assume that, obviously I'm not going to assume, say that the distance from 0 to 0 is 0, but everyone else is infinity. So what another interpretation of infinity is that they are unreachable. So in other words, after I run this algorithm and some of the nodes are still infinity, what that means is those nodes are not reachable by the node 0 or our source vertex. Okay. All right. So what are we going to do? What we're going to do is, again, the same thing we did before. We find the links from 1, 7, and 4. Okay. Now, so what we do is then we update the distance to 1. We know that we thought the distance was infinity to 1, But now we find a distance which is 5. Okay, we process that edge. We say, okay, distance to 1 is 5. But where did we come from? We came from 0. Okay, we came from 0. And we do the same thing with this one. We thought the distance to 7 was 8. But now we find a shorter one. 7 was infinity. We found a shorter one, so that's 8. But I came to 8 from 0. Okay, same thing with the distance to 4. We thought it was infinity, but we know we can find a better estimation, which is 9. And then we came to that from 0. Okay. So the next thing I'm going to do is I have what's called a priority queue. In the priority queue, I have 5, 9, and 8. Okay, those are the distances I have, and the other distances are bigger than their infinity. Okay, so from the priority queue, I pick the next smallest thing. So it's a min priority queue. Okay, so I pick the, hold on, what did I say here? No, I made a mistake. So I have the nodes 1, 4, and 7. That's what I have. Okay, nodes 1, 4, and 7. Because they have distances 5, 9, and 8. And the node 1 has the next shortest distance. It's 5. So what I'm going to do is I'm going to remove that from the queue. And then I will go to node 1, because I removed it from the queue. And then I'll see if I can update 3 things. One is that, let me show you by using color. You become more clear by use color here. So these are so if you look at those 3 nodes, those are the nodes that are connected to 1. Okay, so now I can update the node 3, node 2, and node 7. Right? So what should the distance to node 3 be? Okay, so someone said node 3 be 20, 20. Yes, so node 3 is going to be, could be 20. Okay, but how did I come to 20? I came from node 1. Okay, so it's the distance to node 1 plus the new distance. Okay, and what about node 2? Right now, node 2 is infinity. $17. Okay, so I came to 17 from node 1. Okay, and node 7. Do I have a better distance to node 7 than 8? No, because it's 9, right? So if you take the node distance to 1 and add 4, that would be 9, but that's not smaller than 8. We already have an 8. So therefore, we are done. Okay? So now what we're going to do is we're going to pick the next thing in the smaller things. Okay? So the next smallest node, the distance would be, so this is done, this is done. I'm going to put a correct mark here to say that I have processed them. Okay, so in my priority queue now, I have 17, 29, and 8. So what's the next node I should pick? 7. Okay, because 7 has the smallest of the distances so far, right? Other ones, the 0 and 1 are processed, so we don't touch that. So now from 7, I can update 5, right? I can update 5 to what? 14. Because 14, I came to 14 from 7. Okay, and from 7, I can also update 2. But if I come to 2 from 7, what would be the distance be? 15. So should I update? Yes. Okay, so right now the distance to 2 is 17. So let's update to 15. And instead of 1, we'll say 7. Yeah, because we always put the update as it's a shorter distance. So we found something better. All right. So I think we did that. So we process this edge, this edge. There are no other edges going out of 7. Those are the only 2. So I'm done with 7. Okay. So now what is the next node I should pick from the priority queue? Okay, so the next node should be 4. Okay, so that's the next node I'm going to pick. Because 4 has the lowest distance among the remaining nodes. All right, so I pick 4. Okay, I pick 4, and then I update 6, right? Because the distance to 4 is 9, plus distance to 6 would be now 23, and that came from 4. Okay, so I did that, right? So I did update using this edge. It's good to update, cross out the edges, because, oh, it is 29? Oh, yeah, thank you. 29, you're right. Why did I say 23? Okay, 29, yes. Okay. And then we look at this edge. Can I get a better distance to 5? Yes, so we can get a better distance to 5. That would be 13. Okay, it's 9 plus 4. And we came to that from node number 4. So we update the edge to 1, 2 as well. Okay, so we process that. How about 7? 7 is still, no, 7 is considered, so we don't have to worry about 7. 7 is out. So I'm going to darken these things that are already been selected. Now we are kind of working with 4. We darken 1. Okay. So the things that have dark circles are the ones that are already being processed. So I think that's it, right? So the next, what is the next node I should select? Yeah, node number 5. Okay, that has the lowest among 15, 20, 13, and 29. Okay, so let's take node number 5 and pick that. Now, so the question is, can I get a, so clearly I probably can update 2. Can I update 2? Yes, so I can update 2, right? Because using the edge from 5 to 2, it's 14. So now this becomes 14, and oops, not this one. This becomes 5. All right. And so that's good. What else I can update? Can I update 6? You look at all the edges from 5. Okay, now distance to 5 is 13, and then from 13, if I use this from 5 to 6 node, I can get 26, which is better than 29, right? Is it 26 or 25? Yeah, it's 26, right? How'd you get 25? 26 is okay? So wait, how'd you get that? wait. So I have 5, which is 13, plus 13 plus 1. Where'd you get 1? Yeah. We'll get to that later. Okay. Right now, don't worry about that. That 11, you shouldn't worry about it. Okay. So you shouldn't look ahead too much because this is an algorithm. Okay. So so right now I can do better. I can do 26 using this link here. Okay, for the 6, and that came from node 5. All right. So right now 26, although we know we are going to settle at 25. Okay, we'll just wait. Anything else I can update? No, right? Okay. So now what's the next node I'm going to relax? Two. Okay. So we're going to choose 2. Okay, now I find that the distance to 2 is 14. Plus, if I add 11, I get 25 to 6. So I can update 25, 6 to 25, and this is going to be 2 now. It came from 2. So I found a better distance. All right. And can I update 3? Okay, I can update 3, right? Because the distance to 2 is 14, plus 3 gives me 17. So I could get a better distance here. So that's 17, and it came from 2. All right. Anything else? I think those are the only 2 edges from 2, so I'm done with 2. So the next one I'm choosing is 3, right? That's because I have 2 things left, 3 and 6. So I'll choose 3. So from 3, if I update anything, it's 6. Can I get a better distance to 6? No, right? Because distance to 3 right now is 17. And if I add 9 by processing that edge from 3 to 6, I get 17 plus 9, which is 26, but that's not smaller than 25. So there's nothing I can do there. Okay. So at this point, I'm done. All right. Because 6 cannot do anything. 6 is done. All right. So what we did was we essentially found the shortest distances to the nodes. Okay, also we found where those things are coming from. In fact, using this, I can find the path back. All right. So the algorithm for doing this is, I mean, there are many ways to implement it. All right. So one part of the algorithm here is that this is one way of doing it. But there could be other ways of doing it. Your book might suggest some other method. That's fine. Okay, it's just different ways of doing it. So here, E is an edge, and V is the, if you have a E edge, in this case, V and W, V is the from edge, and W is the to edge. I mean, W is the to vertex. Okay, V is the from vertex, and W is the to vertex. So what this does is to essentially do that distance calculation. It says distance to W plus distance to V, because what we get is some distance to 2 things, all right, plus the weight of the thing. So let's say that distance to W is like, I don't know, 10. Distance to V is 5. Okay, this is what we know so far. And then let's assume that there's an edge weight from V to W is 2. So what this says is that distance to W, which is 10, and you compare it to distance to V plus the weight of E. So should we change the distance to W? So my question is, should we change the distance to W based on this? Yeah, so we found a better path, correct. So the 10 should be changed to 7 because it's the distance to V, which is 5 plus 2 gives you 7. Okay, so that's really the algorithm. Now, this algorithm is big O of 1. It's just if whenever you call relaxing an edge, that means you look at the edge and consider whether the distance can be reduced. So here's the main priority queue algorithm, Dijkstra's algorithm. So what we do is we put all the vertices into, we assume that distance to the source vertex is 0. Everybody else is infinity. Okay, the Java infinity. And then we also have a priority queue. Okay, so what we do is we insert the source vertex with the distance 0 into the priority queue. While the priority queue is not empty, we take the next minimum. If you recall, that's what I did, right? You take the next minimum, and then you find all the edges connected to that next minimum. That's what we did, right? So when we find a minimum, and when I made it dark circle, I found all the edges to that. Okay. So and then we do we process this. Okay. So the question we can ask is, what is the runtime of Dijkstra's algorithm? Okay, so it turns out that the following. This is the way you can think about it. Now, this part, the while loop, is big O of V. All right, and the delete min. What is the delete min complexity from a priority queue? It's a priority queue of vertices. Log V. Okay, so delete min is log V. And if you look at the while loop and the delete min, it gives you V log V. That's one part of the formula. Okay. Now, the other part of the formula is that every time you get something, you have to relax the edge. Relax the edge means that every edge that you get, every edge you find in that adjacency list of V, you will have to relax it. Okay, so we are looking at the every time you get an edge, so we get E edges to worry about. Okay, we have to worry about E edges, but whenever you have an edge, you have to go to the priority queue because you might update something in the priority queue. Okay, you might update something in the priority queue. So that requires log V operations. All right, so it requires log V operations because priority queue is a priority queue of nodes. So we can update it with the log V operations. So it turns out that the Dijkstra's complexity is this. So it's roughly proportional to slightly more, a multiple, essentially a multiple of the BFS, right? That's BFS. So it's like a log multiple of BFS. Because log is not that big, we are okay. So for example, if you have a million nodes, right, and the Dijkstra's will run in about 20 E plus V, because the log of million is about 20. So Dijkstra is going to run in that time. Okay. Now, surprisingly, the person who invented this algorithm, he was I believe he's Dutch, and he is I believe he also invented Pascal language. You're probably not familiar with it. And if we didn't have this, we will not have Google Maps. We will not have any kind of shortest path algorithms that tells you exactly how to go from X to Y in the shortest way. Now, you might imagine this has a lot of applications in Amazon and other kinds of businesses, because they have to optimize the path they go through, like UPS or FedEx. Okay, so they can optimize the shortest path based on the traffic or the distance or whatever the other factors. So it gets complicated. But what the Dijkstra showed was that it's really, you can really do it nicely. You don't have to do it in factorial time. Because if you look at the traveling salesman problem, that is still very hard. Okay, but the Dijkstra's, if you start from a single source, and it can find all the distances. Now, one thing that is necessary to notice about the Dijkstra's is that Dijkstra's, if you really want to find the distance from one node to some other node. So let's suppose that in this graph, we are only interested in finding the distance from 0 to 2, right? We're not interested in finding the other ones. But you can show that there's no other way to find the distance to 2 without computing the distance to 1, 7, 4, 5, 3, perhaps even 6. Okay, so there's no canonically easy way to do that in Dijkstra's. In other words, when you try to compute the path from one node to the other, you might end up computing all the shortest path from that node to every other node. Okay. Now, clearly, it's the single source shortest path, right? So if you think about all source, okay, all source shortest path, what would be the complexity be? Like, suppose I want to find the shortest path from every node to every other node. It's a lot of work to do, right? Let's see if you can come up with the answer to that. What is the complexity of, okay, V times log E plus V, right? Other ones? V log V plus V. Okay, good. I like that. So essentially, all you have to do is just multiply this by V. Okay, so it almost becomes quadratic in terms of V. Okay, so we can say this is V log V, E times V log V plus V squared log V. So it becomes very complicated. All right. And, you can make certain assumptions about that and so on. So this is really very, very important, and I have something for you to try, okay, later on. I don't know, maybe it's the same thing I did. I did the same thing. 5, 6. Yeah, I did this. Yeah. I think I did the same thing, right? Yeah, I did the same graph. So you could, I put a new graph here. Oh yeah, this one here. I think you should try this one. I won't do it right now because we don't have time. Okay, try to find the shortest path from A to everyone else. Let me show you a few things about this. And these are the complexity of implementation of priority queue of the Dijkstra algorithm. And what I discussed was the binary heap implementation. Okay, binary heap implementation. And here you only see E log V because I think you can drop some of them because they're just too big. I think what we had was like V log V plus E log V. Okay, because V is typically a lot smaller than E because you have a lot more edges than vertices. And therefore, you can kind of absorb this. This is roughly E log V. Okay, so you can, E log V can absorb that term, V log V, which is smaller compared to E log V. There are better ways to do this. So people have improved this over the years, like Professor Tajan, who teaches at Princeton, has come up with an algorithm in 1984 to improve the convergence of this Dijkstra algorithm to V log V plus E, which is very good. Okay, so it's much more efficient. It uses something called a Fibonacci heap, not a binary heap. It has different properties, and you can Google that and find out. Okay, so the last thing I want to tell you is there's a proof of correctness. In other words, how do we know Dijkstra's find things? Now, there's one important thing about Dijkstra is that in order to use Dijkstra, all the weights have to be non-negative. Okay, so you couldn't have negative weights. You might imagine a graph having negative weights because you might imagine a graph having a negative cost, right? So you can have a graph with negative weights. That's possible, right? So for example, you might say, to transport something from one node to the other, it costs me money. I don't make any money. So it cost me $2. I lose $2. Yeah, I gain $3, right? You couldn't apply Dijkstra to this one. All right. So the proof of correctness of Dijkstra's, which is proved by induction, which you probably did that with the discrete structures, is based on the fact that Dijkstra has non-negative weights. Okay, let me pause here. You can't. I think the problem with the negative paths is that suppose you have negative weights, like so take something like this. So suppose you have negative weight. Okay, what is the shortest path from S to T? Shortest path from S to T. -3? No. Okay, let's suppose you have a graph like this, right? So that's my last question, sort of. What is the shortest path from S to T? You could say -3, but you can also say more, right? You can find a shorter path than that. I'm not talking about simple paths, right? In other words, you can say it's -6 because you can go another round. Okay, So in fact, the shortest path from S to T here would be negative infinity, because you can just keep going, all right, to get a shorter and a shorter path. Therefore, the shortest path does not exist in this case, right? So if there's like a sort of like if you have like a cycle with a negative total weight, that's the fact you're looking for. You have a cycle with negative total weight. There's no shortest path. You can just keep going. It's minus infinity. Okay. All right. Let me pause here. Stop here. You guys are free to leave, or I will be here a few minutes if you want to ask questions. I am doing good, thank you. I'm very bored at home anyway. I'm really hoping that the fall semester that we will go back, but I'm not sure yet.